The letters. Oh, I'm not sorry.
Oh, yeah. It's kind of creepy. Anybody else got him like second guessing what you're going to say or do? All right. Okay. So, chapter 4, I'm going to be real excited about this. Chapter 4 gets into a little bit of the physics of the universe. Do these galaxies look like they're dancing?
A little bit.
A little bit. Did you guys know that some of us have seen the Andromeda Galaxy through a telescope? Okay. Andromeda Galaxy, some of you guys know, is actually going to run into the Milky Way galaxy. Andromeda, a little bit bigger than Milky Way. 2 galaxies. Why do you think they do that?
About run into each other?
Yeah.
Because they're on a collision course?
Because they're on a collision course. And one of the things we know, and actually Newton said, that things don't move like that unless there's some force driving them. When 2 things come together, well, I'm after gravity.
Well, I mean,
The force of gravity.
Are they pulling themselves towards each other, or were they already on the course to hit each other?
That's a good point. Maybe a little of both. Maybe they kind of got nudged. That happens all the time with comets that are outside, or way out there, like not going to bother anything. And the comets kind of come close enough to Jupiter and get kind of a gravitational nudge, and they change their trajectory. So it's gravity, people, making this dance, and gravity that's going to make our galaxies merge. Okay, and gravity is a physics thing. Okay, astrophysics. That's what we got going on here. So I hope we're gonna. I think maybe I'll try to get this up a little bit. So Sir Isaac Newton, we're going to talk about. You guys started with the letter K. Who was the dude who talked about how the planets move?
Kepler.
Kepler. Very good. Kepler came up with 3 laws. Newton comes up with 3 laws. Okay, Kepler was before Newton. Kepler's laws were just about the planets, but you know what? Newton's 3 laws also can talk about the planets, and kind of it works out real well. Okay, so Newton actually. Anybody in here love calculus?
I got a question.
Oh, what is calculus? Oh, I know. What kind of well, you can blame Newton for that. But all right. So, physics. Dancing galaxies. How cool is that? Okay. Moons that orbit planets. Planets that orbit the sun. Okay, what is that? What is up with that motion? We're going to kind of talk about that motion. But in physics, and actually they kind of call it like mechanical physics, the whole movement of stuff. Okay, we got to talk about some terms. One is speed. And if you're saying how fast something's going, you basically say it went a certain distance in a certain time, and you do the division, right? Okay, so we could say in 1 second something goes 10 meters. Its speed is 10 meters per second. Well, velocity is a little bit different. Velocity does the whole speed thing and also gives direction. Okay, that's an important distinction. So we could stick with the 10 meters per second, but if we go ahead and throw in direction, now we have velocity. So speed and velocity are not the same thing. Speed and velocity. Which one's more complicated?
Velocity.
Velocity has more information, exactly. So the last thing we need to, in order to kind of make today's discussion work for us, talk about acceleration. Now, we're all probably, if you were going to ask a little kid what acceleration is, he'd probably go, okay, he'd go from in his imaginary motorcycle from 0 to a certain speed, okay? Acceleration is changing your velocity, but remember, velocity is complicated. Velocity has 2 what we call components. Velocity has how fast you're going, and velocity also has what direction you're moving. So if you change any of those 2, you're accelerating. Are you accelerating if, and now the little kid might not know this, but if you go, are you changing your speed? You're going from really fast to basically 0. You're changing your speed, you're changing your velocity, both. Okay, so that's a form of negative acceleration. That works too. You know little kids, right? So here's some pictures to kind of show you acceleration. This is the dude. You can kind of see the little red truck, little red car, going from 30 kilometers per hour to 60 kilometers per hour. Okay, is it changing its direction? Nope, just changing its speed, but it's accelerating. Okay, now it stays 60, but it's going in a curve. Okay, the way you kind of look at this, and we're going to have to kind of get used to this convention, is, let's see if I can do this. This car right here, okay, is going like that. This car is going like that. This car is going like that. Okay. So ultimately this car over here.
Showing up on the screen
Oh, thanks. It's been doing that. Did they Monday too, didn't it? Discard. But as it turns, I was trying to show you. Okay, let's just pick this car right here and try and take the middle of the car, and it's going like this. And let's take this car right here and take the middle of the car, and he's going like this. And this car right over here, kind of before the end, and he's going like this. Okay, so can you see where the direction of those arrows is changing? Still 60 miles per hour, and you guys buy that this is accelerating. Why is it accelerating?
Changing direction.
Changing directions, exactly. Okay, I'm going to go ahead and fast forward to something we're going to get to, and we should get out of here early because I only want to get to kind of halfway through these slides. So what's this? The sun. Okay. And what shape is the orbit of the planets? Ovals, ellipses. Very good. Okay. Case in point, if we, and I realize that, and are we going fastest or slowest when the planet is closest to the sun? We call it fastest. Very good. Kind of remove that from it. Let's just assume we're going a nice, easy clip. Okay. But can you see where, based upon this, if we were going the same speed, okay, the whole time, I'm a planet, I can be Earth, okay, can you see where actually we're still accelerating? Why are we accelerating?
You're changing direction.
Because you're changing direction, exactly. I could add to this planets, smiley face. Okay, planets as they orbit the sun are accelerating. All right. So one last one on there is the car is coming to a stop sign. So it's de-accelerating, which kind of seems like an oxymoron. De-acceleration is negative acceleration. Did it change its direction? No. Did it change its speed? Yeah. So it changed its velocity. Okay, and so it is accelerating. Okay. So we had Kepler's 3 laws test question, right? Did you catch that? Subtle. I made out the test, kind of. I have it outlined. I'm so excited. Okay, so Kepler's 3 laws, Newton's 3 laws. Be able to at least list them. Do you get to have a note card with you on your test next Wednesday? Yes. Okay. So Newton's 3 laws, I love them because they make sense. Okay. So his first one basically says that an object that's in motion will stay in motion unless it's acted upon by some other force. Okay, so thus the, how many people in here saw, what was that one where the astronauts were, it's fictional, and it was really good, beautiful music, and she lived and he died, but they were stranded out there. Oh, so cool.
With Cinderbolt.
Yeah. And she lives. But if you,
Gravity.
Gravity, thank you. Gravity, exactly. Gravity. So I've heard Neil deGrasse Tyson kind of rip that movie apart. He liked it, but there's a lot of science that wasn't exactly right. But, you know, you got to kind of. But the thing that they tried to do in that movie was basically say, look, if you're an astronaut and something leaves your hand, okay, basically it left your hand and you imparted a force on it. After that, it's going to go at constant velocity. Whatever speed and direction it left your hand with, it's going to go on forever unless it hits something or you go ahead and use some other force to deflect it. So that's what this little space shuttle thing is showing you. Okay? In outer space, there's nothing to slow you down. There's no force to change your direction. Okay, so a few years ago, and I think it was a woman astronaut Ch4, like up in the International Space Station. She might have been fixing the Hubble Space Telescope because they've had a few missions to fix that thing, and she lost a hammer. So there you go. You know, it's gone forever. This is just not a happy camper this morning. Okay, that's his first law. Something in motion will stay in motion, that exact same motion. That would include speed and direction unless acted upon by an outside force. This other one says, well, if you have an outside force, what's it going to do? Okay. Well, if you have an outside force, come on, reconnect, you silly. Okay. So, what could you say about that ball? Is that ball gonna, what could you say about that ball's motion after it leaves his hand? What's its motion as it's sitting here? I mean, what's its velocity? What's its speed, I guess I should say?
0.
Its speed is 0, exactly. Okay, and so it's gonna accelerate, it's gonna go faster, right? Here there's these things about, you can make, if you know how to put little, you can put little swirls on it, okay? So we have all sorts of physics going on with that ball. Now, if the batter was not going to hit that ball, let's just say he threw a wild pitch, okay, and came nowhere near the batter. Is it going to go on forever, like in outer space? What's going to stop it?
Gravity.
A couple things. Gravity, exactly. That's the big thing. And maybe friction of the air, and maybe it hits a fan or something, you know, it will eventually stop. Okay. So according to Newton's second law, F is equal to ma. Okay, where F is force that's acting on an object. That object has certain mass m. I guess that should be lowercase m. Okay, and that object is going to change its velocity. Remember, velocity can be, the change in velocity could either be a change in speed or change in direction. Okay. So to me, the way I think about this, just one more time, is you apply the force, and you see the acceleration. The mass is just kind of there for the ride. Put another way, if you see the acceleration, you can calculate what force must be going on. Okay, so we can kind of all do some different things with that. Okay. So in that F is equal to ma, a couple different things. There's this A, actually we're going to call it a little g. Some of you guys have learned. Little g is, if you look at if something's going to fall to Earth, okay? So, and I'm going to show you some examples of this, okay? But if something's going to fall to Earth, the reason it's going to fall and not just float around is because of gravity. Every object on Earth, that chair, that pen, us, actually is in kind of a battle between the Earth and the mass of that object. Okay, I'm going to kind of show the universal gravitation equation coming up. But stuff falls due to gravitational influence of the Earth. Okay. So, and this actually is a test question of sorts, okay? Because like I said, that test is kind of on my mind. Sometimes instead of 10, it's 9.8 meters per second. Each second, S stands for second. 10 meters per second, each second an object falls. It's going to go faster and faster and faster. Okay, so that's why if you're like into tracking your units, that's why this second and this second can combine. And that's why it's also known as 9.8 meters per second squared, per second. So it's going to go faster and faster and faster. So instead of the guy pitching the ball with a certain force with his arm, we're just going to be lazy and we're going to drop something. Okay? And so here we go. Let's kind of think through that. Road trip. Okay. Oh, it didn't do it over there, did it? Okay, that's okay. Okay, so this is kind of scary. A man on top of the roof in a green hat, but don't worry, nobody panic. So he's going to drop an object. Now notice that the influence of the gravity of the Earth and how fast something's going to accelerate, how much it's going to accelerate, is independent of the mass of that object. And actually that's one of the things that Galileo came up with that Aristotle was wrong about. He said, and most people do say, if you drop a hammer, it's going to fall faster than if you drop a feather. Actually, hammer and feather, that little experiment was done on the moon. They're going to accelerate, go faster at the same rate. So here we go. At time 0, the velocity is 0. And we're just going to kind of go ahead and say it's all in one direction. Okay, so all this changing is the speed. The direction's the same. So when 1 second has elapsed due to this force of gravity, it went from 0 to 10 meters per second. When 2 seconds lapse, okay, it gained another 10 meters per second relative to the end of the first second. Okay, so you add 10 plus the 10 it was going, so now it's going 20 meters per second because 1 second elapsed. What if this was 3 seconds elapsed down here? How fast would it be going? T is equal to 3 seconds. It picks up 10 more meters per second, so it's going to go 30 meters per second. Okay, so if we let T be equal to 3 seconds, okay, down there, the speed or velocity is 30 meters per second. And I'll try to, on Friday, bring just some objects. I don't know how, interested, or how, not interested, but how complicated we could get about this. But if you just, and you have to be careful of aerodynamics. You take two objects that are similar with regard to how they're going to resist the air, or the air resistance as they fall. Okay, and they're going to fall at the same rate. I just think that's neat. I don't know if you're convinced, but okay. So that special thing of dropping objects to our Earth's surface. Now, the acceleration due to gravity is going to change if you're the closer to the core of the Earth you get, or if you're above the Earth's surface. But just in general, 9.8 meters per second is how much it's going to pick up speed for each second it falls. Okay. So let's see if this works for us. Now, this is not science fiction. Hey, if the camel can work for us, you would think that this little NASA video would work for us. I should have asked how many people think that we never landed on the moon. And I get those people in this class, but I do believe we landed on the moon. I think it's a hoax. It's a short video.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo. A long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to do for his findings on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather, or a falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Jumping around. Okay. So do you buy this, that how much air is there on the moon? How many air molecules? The atmosphere is basically negligible. The Earth has an atmosphere, the gas that's hanging around the Earth for a long time, nitrogen, oxygen. It's pretty small, actually. But the Earth has that because we're massive enough. The Moon has an exosphere. It's like instead of having gases that are stuck to the Moon, because of gravity, actually it's just kind of oozing a few gas molecules here and there. Poor thing. Okay, it's like outgassing. But the reason this was ideal to do it here is basically you don't have any air resistance. I mentioned that you have to make sure your two objects are aerodynamically similar. Okay, you didn't have to worry about that. Do you think the Moon has gravity, though? It has about 1/6 the gravity as we do here on Earth. Okay. Alrighty. Okay, so here's our two masses. Well, you can be the green thing or you can be the gold thing, but these are two objects that, and all two objects have this sort of mutual, you can see the blue arrows are showing attraction. So this is kind of the mutual attraction all objects have for the Earth, okay? But this just happens to be, they're kind of similar in sizes. So we say that, I bet you buy this, that the closer the objects are to each other, the stronger that gravitational field they talk about, okay? If you take the objects and make a bigger distance between them, that gravitational field is less. It's kind of like if we were to go above Earth's surface significantly, the acceleration due to gravity would be significantly less, okay? Less of a pull. So we say that, the other thing though, I guess number 2 says, if you get, the more massive they are, the stronger the pull. And almost, this is intuitive, so that's what number 2 says, okay? And then number 3 says, if you get them farther apart, then their gravitational field decreases. So we have, it looks like a busy equation, right? But if you kind of break it down, and in physics they do a lot with equations, okay, but if you kind of break it down, up here, can you see, so what's M1 and M2? What are these?
The mass of the first object, the mass of the second.
Exactly. So if we increase this number, okay, which we're going to divide by the distance that was squared, G is actually a constant. We do a lot of that in science. So G is fixed. Okay, so the things that you can change are the masses of these objects and how close they are. So if you increase either one of these, what happens to the force of gravity, which is F sub G?
Increases.
It increases, exactly. Yep. Okay, well, let's pick on the D squared down there. What's D?
Distance.
Distance. And these are test questions. So, hey, it's kind of fun. I love having the test made out, or mostly made out. So if you increase the distance, what did we say was going to happen to the field of gravity between those two objects?
That's not going to be as strong.
It's not going to be as strong, exactly. So as we increase the distance, the fact that we are dividing by that, can you see where you're dividing by a larger number? What happens if you divide by a larger number? It gets less, exactly. Okay. So we say that up there at the top, we do this all the time also, we say that with regard to the masses, okay, if you increase the masses, it increases the force. We call that a direct relationship. Okay. With regard to the distances, okay, we said if you increase one, you decrease, oh, it's not writing, is it? If you increase one, you decrease the other. Okay. And that's an inverse relationship. Okay. So, this is kind of a fun little topic. The subtle difference between mass and weight. And I'm not going to hold you to this. Recently, we talked about the whole theory thing. I'm going to hold you to that. I want you to go out and tell the world that the phrase in general, that's just a scientific theory, is wrong. Okay, that's just a scientific theory. Okay, you could say that's just a hypothesis. Okay, but this one, okay, mass and weight are not the same thing. Mass basically is the amount of matter an object contains, and that would be going back to that number of atoms and stuff like that, and we're not going to like count atoms in here, okay? But weight basically then has to do with the gravity is acting on that mass to create a weight. A weight is actually a force. So as you step on the scales in the morning, oh, I hate doing that, but I do anyway. Okay, as you step on the scales in the morning, okay, you are, there's an interaction between the earth and you are putting a force on that scale. Okay, so that's your weight. So the force would be actually pounds, okay? The mass is like how much matter you got, and the acceleration in that case would be the acceleration due to gravity. Okay, so here we go. Speaking of, here's the dude in the green hat again, all right? Guy that was gonna throw the thing off the building. He sure gets around. So let's say, for whatever reason, he wants to weigh himself in an elevator. Okay, so I'm gonna show you some situations kind of from left to right, the dude in the elevator weighing himself. And so what you need to do is kind of look at that dial up there. Okay, so right now, he's weighing, oh, he's kind of light on the light side, I think, 140 pounds. Okay, his weight is normal. So let's go ahead and change it up a little bit. And let's go ahead and give that elevator a little bit of motion. We're going to have that elevator move up, but we're not going to have it move up at constant speed. We're going to have it continuing to go faster and faster and faster and faster. We're going to have it accelerating. That's important. Okay, because honestly, we've all been on elevators before when there's that initial, goes from 0 to, I don't know, 5, whatever it is, miles per hour. 0 to 5 miles per hour, that's when you feel that. But then once it's 5 miles per hour, you're like, oh yeah, that's just normal. Like, there's no acceleration. It bottoms out. It gets to constant speed. So let's say it keeps accelerating. So can you see what happened to the guy's weight? It got more, yeah. So, because now not only does he have the force of gravity, but he also has this acceleration of basically the scale up, coming up to meet him. All right. So let's change it a little bit and say somebody's, and this happens all the time in the movies, somebody's up there and they snip the cable. Okay. So they snip the cable because that's one way to go ahead and get the cable to begin just falling to the earth, accelerating at that 10 meters per second each second. Okay. So it's falling, and the thing here is, to me, his weight should be basically 0 because he's falling and it's falling. Oh, I guess this next one is free fall. I don't see a big difference between the third and the fourth. But you see a little snap in the cable, and they're both basically falling through space. And see, to me, with regard to how much force does he create on that pan so the dial can go up, nothing. Okay? He's chasing it down. Free fall. I'm free. Right, okay. All right. Okay. So, you guys, a few things. You guys told me that as a planet orbits the sun in a circle or an ellipse, we know planets orbit in ellipse, I'm changing direction. So even if I am kind of going at the same speed, I must be accelerating. Okay. So orbit is a type of acceleration. But I'm going to see if I can kind of convince you that an object, that blue line right there, is actually going to be the path that this guy has a little, like he's going to fly through space. He's going to take that path, okay? But before he takes that path, okay, he's going to do a few things he probably shouldn't, okay? Now, the problem with this scenario is he basically just walked off, okay? But the thing is if he walks faster and faster off the plank, heck, if he goes ahead and puts on a backpack that lets him take that plank and go, just like, oh, what was that superhero that, there's all sorts of them that had the pack, I'm trying to think, what? He's a jetpack, yeah, but like he wore red outfit. Anyway, okay, yeah, he did that, okay? So here's the deal, and I really think you should think of it this way, okay? Think of it like there's, in physics, or not necessarily in physics, but we kind of talk about two things going on at once. So for instance, this guy, he went this direction, but he also has gravity coming, you know, he hasn't left the gravitational pull of the Earth. So these two added together kind of puts a little curve on there. Okay? So we could watch him later on in his journey. Okay? So at any point on here, we could go ahead and kind of say there's two things going on. There's his initial, because according to Newton's first law, an object in motion will stay in that same motion that includes direction and speed unless acted upon by an outside force. So he's kind of got that original going on for him, okay, that put him into orbit. Okay, that energy that put him into orbit is still there. So he's got that, and then at every point he's also got this. That's the pull of, that's his interaction with the two masses interacting. So what's it do? It kind of has a curving sort of deal. Okay, so two things. So that's why we say that he is actually falling. He's falling to the Earth, but he just kind of misses the Earth, but with his original energy that sent him out that going like that. Okay. Happy dude, happy dude. I was thinking about this, and my mom was like, oh, did you hear that, like, in Japan or something, that something fell to the Earth recently? I need to look it up. And anyway, she was like, oh, really, Mom? No, she keeps track of these things. But have you ever heard of something in a decay orbit? Okay. So the thing about it is there are air particles up there that are interacting with the object that's trying to orbit, who had that initial thrust to put him in orbit. So with that friction, it does slow down, and it will eventually lose its okay, and will fall. Okay. Yeah, I think I'll probably come back to that on Friday. Okay, so that's Newton's two laws. The first law, something in motion will stay in motion. By the way, the first law, and I think it probably went something like this, something at rest will stay at rest. That's also his first law. And I think of my kid every morning when I'm like, dude, you're at rest. This is not good. Okay, something at rest will stay at rest unless acted upon by an outside force. And then his third law says that for every force out there, okay, you take a force, the dude throwing a ball. For every force out there, there is an opposite force that is in opposite direction but equal in what we call magnitude. So the example here is, looks like a space shuttle being launched, and the force, if you read your textbook, basically this thing, the thrust, the thing that got this thing moving, was the force. It's a chemical reaction that basically has a force going this way and a force going that way. So the two forces here, and it's a chemical reaction, a burning reaction, a force going that way and a force going that way. Okay. I'll have to look into that. Okay. Maybe I could just write on the... No, I don't think so. All right. Next slide. So Newton's three laws. You want to be able to say them. And honestly, for Newton's second law, if you just do F is equal to ma, I'm cool with that. Okay? All right. So momentum. So you have two objects, a bike and a truck. and the bike is traveling slower than the truck. Okay. And of course, you guys would tell me you'll take your chances with the bike, right, to get to hit you. So there's this thing called momentum, and what momentum basically is it's equal to the mass times the velocity. I don't know why it keeps freezing on me. Mass times velocity. It's coming up. So with regard to mass, truck's got the bike beat. With regard to velocity, truck's got the bike beat also. So if we look at both of those terms, you can see that the truck has both more mass and it's going faster. So it's got more momentum. So, you know, you might have even used this term momentum in kind of casual conversation. You sit down at night and you're like, oh, I lost my momentum to do anything. I'm still the same mass, but I'm not moving. So, and in the universe, in science, in reality, things like momentum and energy have to be conserved. So you can't take a certain amount of momentum and it just goes away. It goes away, but it went somewhere, okay? Something got accomplished in case of you losing momentum at night, or you transferred it to somebody else. It's like, here, take my momentum. Okay. So in the case of the bike, the force that made the bike go, what do you think? The dude's consumed a cheeseburger that day, and he turned it that chemical energy into his muscle, and then mechanical energy to move the bike. Okay, and then ultimately the momentum of the bike. The thing with the truck, he was burning fuel, so creating a net force that ultimately created that velocity that is balled up in the momentum. So there's straight momentum. This sounds kind of like straight momentum, doesn't it? Like with the bike and the truck. And then there's angular momentum. Angular momentum has to do with circles, something moving in circles. So angular momentum introduces one term that straight momentum doesn't. So I mentioned, this is kind of clever, I think. So just kind of soak this in. We have the whole red box and the blue box, and I could say, which box are you, red or blue? Notice the red one's moving and the blue one's not. Okay. So just a simple multiplication. Can you see momentum is speed, 4 meters per second, times the mass, okay? This guy's speed is 0, so how much momentum does it have? None. And I think I'm going to go ahead and bring it up. But have you ever seen those, it's called Newton's cradle, where you have, it's at rest, it's got little balls kind of hanging, and you take one ball and it goes, okay? So what you do up here is you give this ball a certain amount of potential energy, you let it go, and it starts moving. Why is it going to move faster and faster and faster? Because gravity, and but when it hits this, it stops. Okay? And it imparts the momentum through those other balls to this guy over here, and he kicks off. Okay? So that's what this is, basically. So you see that assuming that 1 kilogram red box is going to hit this one that's not moving, and assuming just kind of like with that Newton's cradle, it stops. Do you see if momentum is going to be conserved? That now 2 kilogram mass needs to be going at 2 meters per second. Forget the units. Can you see where you started with 4 and you got to end with 4? 4 times 1 is 4. 2 times 2 is 4. So, I mean, it's not that complicated. All right. So this is where I've already kind of clued y'all in on how this works. The fact that planets change the direction they're moving at all instead of going a straight line means that they're accelerating. And something cannot accelerate unless there's a force acting on it. Newton's second law? Okay, force is equal to mass times acceleration. Okay, this is acceleration. Okay, force here is the force of gravity. In the case of this, it's gravity between the planet and the sun. All right. So I said that things can be swapped out, shared, and stuff like that, but they're always tracked. They don't go away. Conservation of fill in the blank. Conservation of matter, conservation of all sorts of energy. Okay. Conservation of momentum, straightwise. Conservation of angular momentum. So notice that regular momentum, what does angular momentum have that regular momentum doesn't?
For the change in the direction.
The change in the direction and the radius. Because it is changing direction, exactly. And so, to me, and how can we describe, again, I'm going back to circular orbits instead of elliptical orbits, but the way we can describe this change in direction is by the radius between the object and the center of the circle. Okay, the radius. So, we just need to add one more term in there. So let's look at this. What happens if we increase the radius? What happens to the angular momentum? Well, let's put it this way. And actually, the example. Let's say that it's going to be conserved. Angular momentum is going to be conserved. And so that means it's constant. If your radius increases and you can't change your mass, but you can change your velocity, if your radius increases, what does your velocity need to do in order to keep the same?
Increase.
It needs to decrease, exactly. So one goes up, the other needs to go down in order to conserve angular momentum. What happens if you decrease your radius? You increase your velocity. So increase radius, decrease velocity, decrease radius, increase velocity to conserve momentum. So a very good example of that is a skater. This is where I wanted to get, I think. I guess I did use the whole period. Okay, so this scenario, she basically has her mass and has distributed it with a relatively large radius. Okay, and you guys told me a large radius, decreased velocity. Well, she's going to go ahead and make her radius smaller, distribution of her mass. The smaller radius, increased velocity, so she's going to spin faster. And actually, in Unit 2, when we start to talk about how the sun and the planets formed, we're going to talk about the conservation of this sort of momentum. So angular momentum throws in a radius term. Okay, well that's how far I wanted to get. Sorry for the false, oh, we'll get out early. Okay. So I really think I bet we'll knock out this chapter on Friday, but I'm going to stick with homework what we do until you can take your test on Wednesday. There's a good chance then we're going to ease into chapter 5 before your test.